talked about this in class last week, so I don't want to spend a lot of time on it here. But it is important, so I do want to get it into a video in case anybody was absent. And you can think along with this, and it's not going to hurt you in any case. So we looked at rates of change before, and this time what we're going to look at is the summation of small changes. So before we looked at rates of change, and now we're actually going to look at adding up changes. And frequently, we're going to be working with time. So we're going to be looking at time changes, time rates of changes, and we're going to sum time rates of changes in order to find change. So a real straightforward example of this is, during each second, you travel 10 meters. So that makes your rate of change 10 meters per second. And you can turn that on its head and say what that means is every second interval you've traveled 10 meters. So we can plug in a time and then get back the distance traveled during whatever that time interval happens to be. So in a very comfortable way, we can view the opposite of rate of change as summing rates of change. This is a graph of velocity versus time, and it's not drawn to scale, but it is still effective at describing what it wants to describe. The total distance between any two times, between 0 and 1, between 1 and 2, between 2 and 3, and so on and so forth, is really just the area under the graph. The horizontal axis here gives us our delta t. The vertical axis gives us our rate of change of position, our velocity, or our speed. And that product would give us delta x. Right? So we could write this as delta x equal v delta t. And everything naturally would follow from that. So the total distance traveled since the beginning, however you choose to define that, and that is a choice, is the distance traveled during an interval plus how much distance has been traveled before. So in each of these intervals, the distance traveled is 10 meters. However, our starting point has changed. So at the end of 1 second, we've traveled 10 meters. At the end of 2 seconds, we've traveled another 10 meters plus our original 10 meters, giving us 20, and so on. And this corresponds very nicely to our model of our new position is equal to our old position plus our change. Our rate of change times the amount of time that we change. So the area under a rate of change graph is the sum of the change plus some additional value that is the original, in our previous example, position at the start of the interval. So the rate of change of a quantity is equal to the slope of a graph of how that quantity changes with respect to another quantity, in our case, usually time. And the area under a rate of change graph with respect to a second quantity, usually time in our case, is the total amount of change. And why we care, again, as I mentioned in the introduction, is we're trying to predict the future. So we model physical phenomenon using a change model For example, where you are is where you were plus how much you changed. How much you change is equal to the rate of change times the time that you have been changing for. And you'll notice this is familiar, and I can pretty much guarantee you it's not the last time you're going to see it.